Hi everybody, it's Sam, back with another iOS 10 screencast. The topic I'm going to cover today is actually part of Foundation, so it covers all of Apple's latest platforms, including watchOS 3, tvOS 10, iOS 10 and macOS Sierra. The new measurements and units classes allow you to express physical quantities inside your app. A measurement, represented by the measurement class, is made up of a value, which is a double, and a unit. For example, 3 meters would be a measurement of length. Units are grouped together in physical dimensions. For example, the length dimension includes units of feet, miles, inches, meters, centimeters, and light years. Today I'm going to take a look at the basics of measurements, how you can create them and how you can interact with them, along with how you can start to model physical quantities using the measurement system. Creating a measurement is as simple as using the default constructor. Here I'm going to create a cycle ride which has a length of 25 kilometers. So the value, which is a double, is 25, and then the unit, we use the unit length dimension and then select kilometers for the specific unit within there. I can then use the converted to method to change that unit to one of the other units within that same unit length dimension. So for example, miles or furlongs. You can see that 25 kilometers is about 15.3 miles or 124 furlongs. Imagine I know how far along the cycle ride I've already completed. So I'm going to create a distance completed variable and once again represent a value of 13 kilometers with a value of 13 and a unit length of kilometers. I can now perform simple arithmetic by subtracting the distance completed from the total cycle ride length to reveal that there are 12 kilometers remaining. This cycle ride is actually part of a triathlon, so we have components for the swim and the run as well. The swim is 2,000 meters, so once again we'll create a measurement to represent that, a measurement with a value of 2,000 and a unit of type length meters. The run is defined as half a marathon. Now I don't know how far that is in meters, but I can work that out. I'm going to create a new measurement that represents the length of the marathon, which I know is 26 miles and 285 yards. So I'm going to start out by creating a measurement to represent the miles component, so measurement of value of 26 with a unit of unit length dot miles. And I'm going to add to that a measurement with a value of 285 with a unit length of yards. Here I'm adding two measurements together that actually have different units. How can it do that? Since both of these units are part of the length dimension, it converts them back to the base unit, i.e. meters, in order to perform the addition operation. Then I can divide it by 2 to get my half marathon length, and from that I can add all of these three things together to get the entire length of the triathlon, 48,000 meters. Now this is still just a measurement. I can convert it into anything I like, seeing here it's about 26 nautical miles. In addition to being able to do simple arithmetic, you can also do comparisons, so you can see that, yeah, the entire triathlon is longer than the bike ride. Measurements and units lend themselves really well to modelling physical quantities. As such, you can use them to represent real-world physical equations in the form of functions. I'm going to do that now with E equals mc squared, the most famous equation in the world. But what does that actually mean? E is energy, m is mass, and c is the speed of light, all of which are physical quantities that will be represented as measurements. To see this in use, I'm going to take a look at the fission of a uranium-235 atom, which is where it gets split into two smaller atoms. The difference in mass between before and afterwards gets converted directly into energy using Einstein's famous equation. I'm going to create a function, emc2, representing E equals mc squared. The first argument is going to be the mass, which is represented by m, and that's going to be a measurement of type unit mass. And then c is the second argument, which is the speed of light, which is going to be a measurement of type unit speed. And this returns E, which is an energy, so it's going to be a measurement of type unit energy. Really quite simple. And once we're in there, we're going to calculate the value of the energy. So that's let energy is mass. We need to convert this to the SI unit in case it isn't already. So that's converted to kilograms. We take the value of that to get the double, and then we multiply that by the speed of light converted to meters per second squared using this utility function that I created. Then I convert this energy value into a measurement with the unit joules. When you think of the mass of a nucleus of an atom, you don't tend to think of it in terms of kilograms, but instead of AMUs, atomic mass units. These are pretty much the mass of a proton or a neutron. I'm going to create a new unit to represent this inside my code. I'm going to create a new unit called AMUs, and it's going to be from the unit mass dimension. A unit has a symbol and a converter, and the converter is used to go from your new unit type back to the base unit associated with this dimension. In this case, we're talking mass, so the base unit is kilograms. The relationship between AMUs and kilograms is linear, so I can use a unit converter linear with a coefficient that represents the number of kilograms in a single AMU. I created a constant struct that includes all of the physical constants that we need, including masses of the different atoms throughout the rest of this screencast. I can now use this new atomic mass unit to work out the mass of the reactants and the mass of the products. That is, the mass before and after the fission reaction. The difference in these masses gets converted to energy via Einstein's equation. I'm going to work out the mass of the reactants, that is the things that are going into the reaction. And within that we have two things. We've got a U-235 nucleus and a neutron. So the mass of a U-235 is going to be a measurement, and the value, now we're going to use a constant inside my constant struct of masses.U235. The unit is AMUs that we created just before. And the mass of a neutron then is a measurement again, this time with constants masses neutron, again with the unit of AMUs. Then I can add those two things together, so masses reactants becomes mass of U-235 added to the mass of the neutron. The playground puts this at the side, it's 236.05 AMUs. I could do the equivalent calculation to find the mass of the product, but to save time here, I've already got a constant that represents that. So the mass of products is a measurement that uses this constant. The thing I'm really interested in here is actually the difference between the mass of the reactants and the mass of the products, because that's the thing that's been changed into energy. I can calculate that simply by subtracting this products from the reactants. Now I need to know the speed of light so that I can use the E=mc² equation. So I can pull that out of the constants again with constants.c, it's about 3 times 10 to the 6, and the units are meters per second. Now that I've created the mass and the speed of light, I can go ahead and use the EMC2 function that I created before. Notice that the units for the mass are AMUs, and the function knows nothing about them. That's the power of using these measurements. You can see the result here is about 2.8 times 10 to the minus 11 joules. This energy might seem really small. Times 10 to the minus 11? Tiny. The reason for that is because it's the energy released by one single uranium nucleus. It would be far more meaningful to work out how much energy would be released by a kilogram of uranium, like a bag of sugar. To do that, I need to know how many U-235 nuclei fit inside a kilogram. To calculate the energy in a kilo of U-235 in this manner, you first of all need to know how many atoms of U-235 there are in a kilogram. There are 1,000 grams in a kilogram, and there are 235 grams in a mole of uranium-235. Avogadro's number tells you how many atoms there are in a mole, and then each of those has a particular energy. That gives us an overall energy for the kilogram, and I'm just going to convert that into kilowatt hours to give us a more meaningful result. And you can see here that it's about 20 million kilowatt hours. Yay! It's another number that's so big or so small it means nothing. I've converted this into kilowatt hours, which are units that are standard for measuring how much electricity a household uses. So I can now take this enormous value of energy and work out, well, how many average households can we support for a year? The average energy consumed by a household in a year in the US is about 11,700 kilowatt hours. So I can take the energy per kilo and divide that by 11,700 to see that that can sustain about 1,700 homes. Or in the UK, then that'll be about 4,300 homes. And with that, I've come to the end of everything I wanted to cover in this introduction to measurements and units. I make no apologies for the fact that I went off on one about physics and nuclear reactions. I think that's really interesting, and it really shows you how you can use measurements to represent real-world physical quantities. I hope you enjoyed yourself as well, although to be honest, I had so much fun I'm not overly bothered. I do hope though that you will join me again on another iOS 10 screencast. Cheerio!